Okay, folks. Hopefully everyone has got their caffeine and had a bathroom break. So that grabbing the file thing has caused issues for some of you. Don't panic if that's the case. I've just posted in the Discord. You can just go to GitHub and download each file individually. So I'm just going to quickly share my screen and then we'll let Paula take over. So just to show you how you would do that, you would go to this workshops folder on the GitHub, and then I'll just link this in the Zoom chat so you will have it. One second. Where's my Zoom chat? And then, for example, we're going to do this activity one first. You simply click on the file, then you go over to this right-hand side where it says download raw file, press that button. So you're going to need for today, you're going to need activity one, activity two, and then this melt inclusion arcs Excel file and this illusions Excel file. So don't panic if that didn't work. You can just download them individually. Okay, so everyone should hopefully have that activity one file. So what you're going to do is you're going to open it however you prefer to run Python. So there's a variety of ways you could open this in Jupyter Lab, in Jupyter Notebook. Whether you're on Mac or Windows, this is going to look slightly different. So I'm going to share my screen. I am a Windows gal and Matt has a Mac, so we'll be able to see both. So on Windows, if you simply open your Anaconda prompt like this, then you should be able to type in either Jupyter Lab or Jupyter Notebook and just press enter, and that will launch up one of those. Hopefully, I can drag across to show what that will look like. So, this is what it's looked like for me. So this is Jupyter Lab. On the left-hand side, you have your file structure. So you will have to navigate to the folder that you've put these in. You can like click back here, or you can just click on the actual things yourself. And then you're going to double click on the IPYMB itself, and it will open up on the right-hand side here. So that's what Jupyter Lab looks like. Jupyter Notebook, if you instead on that Anaconda prompt type Jupyter Notebook, you can also double click these just by launching Anaconda up itself. Again, you're just gonna double click this once you find it in your file structure and it will appear here. Me and Matt, actually, when we do these demos, are going to be using this piece of software, VS Code. One of the real advantages of VS Code when you're running melts is it tells you how long each cell took to run. And this can basically mean you can plan to, if you know your saturation pressure calculations or your fractional crystallization calculations take on average 10 minutes for the number of calculations you're doing, you can plan to like go have a cup of tea or a break or do whatever you want in that time. So that's why we're going to be running in VS Code. The interfaces look very, very similar. So hopefully everyone has had a chance to open the notebook in those. Matt, do you want to quickly show how to do it in Victor?
Yeah, sure. So I mentioned on one of the emails last week that there is an alternative if local installation is being a real challenge, especially for the Alpha Melt stuff. And so if anyone wasn't able to install Alpha Melt and read through that email, you would have seen that there's a what is known as a Victor server is an alternative for doing this. So the Victor server is essentially, I'll share my screen, a online cloud-based server for code sharing in volcanology more broadly. And so this is kind of what their homepage looks like. To sign up, all you need is a GitHub account and to click on their sign up link and fill in a little Google form, and then you'll get access. This is a good way of doing melts calculations if you haven't been able to do the online installation. You won't be able to get started on Victor straight away unless you've already contacted them, but it is an alternative if the online installation is proving problematic. Once you click on that hub portal link, it will open up this and it just gives you various options as to like how much RAM or CPU usage you want in your kind of server. For most things in this, clicking on
I
the
choose the 7.4, Matt.
okay. So
Yeah.
yeah, I've been able to run things fine on the smallest one, but I'll choose the one with slightly bigger RAM just to make sure we don't run into any issues. And then hit start, and this will open up essentially what will look very, very similar, in fact, almost identical to the Jupyter Lab page that Penny showed you a moment ago when she opened it locally on her machine. So this will open up my own server in the Victor project, and you'll see that I actually have like a few folders already existing and various other scripts that I've already run. But what I will do is I'll go back to this is the main folder and pretend like it's the first time I've opened it. So what you could do in here, a lot of these folders won't exist for you because it may be the first time you open Victor. What I would suggest doing is making a new folder and calling it something logical, like that. And then within that folder, you can then open up a Python 3 notebook. And so if I click on
Matt, show
here,
them how to upload a file. Yeah.
I'm going to.
Okay, cool.
And so on here, you could open up a notebook. And one of the interesting things with Victor is it doesn't have PetThermoTools automatically installed in it. So just like when you're doing it locally, you would have to use pip, if I can spell correctly, pip install PetThermoTools in order to install that PetThermoTools package. And it will go through and in this case, install the latest version 0.3.15 onto your Victor server. You can also upload files onto here by using this plus button here. No, sorry, the upload button, just to the right of it, sorry, here. You can upload files. So we could go through, we could find my GitHub page and and find a file that's actually going to be useful. 1 second. And so that git clone file, I could upload that onto here and then try running that. And this is now running in the Jupyter server. And hopefully if it works correctly, which it did, it will open up a new folder which contains all the activities. It will clone that folder in my GitHub, open up this folder, which now has all the activities in it. And I can now open up that as a Jupyter notebook in Victor and run through. And one of the nice things with Victor is it automatically knows where the alpha melts for Python files are. So that install alpha melts command that you all had to run to do it locally, that step is not needed on Victor. So that second step of the installation is not needed on Victor. It automatically knows where the alpha melts of Python files are because they're permanently stored on the Victor server. So it does remove one step of the installation, running it on the cloud-based server here rather than running it locally. So that is an alternative. If the local installation just isn't working at all, please sign up for Victor, use their sign up form, make a GitHub account, and even if not today, by tomorrow, you should be able to run calculations on the Victor server. All right, hopefully that all made sense. I'll hand over back to you, Penny.
And the other thing for Victor is it is fabulous if you want to use melts in your classes. So Matt and I are both teaching petrology and volcanology classes, and some of the exercises we're doing today, we actually do with our classes. As you know, the installation was a bit tricky for many students who've never run Python. It will just put them off. So all you really need to do is get your students to sign up for the Victor server, like probably a week in advance, but often a few days is enough. And then you can get running melts calculations in your intro or advanced classes. We've never had any issues with it. So it's a really, really good resource for getting students started. Okay, I am going to go through now just a basic introduction to some of the things you might want to do. Sorry, I've got way too many things up in Python. And um, show you approximately how to run. And I know some of you are Python experts, and that's fine. And this is going to be a little bit boring for you, but for those who aren't, this will be useful. So I'm just really struggling with Zoom. It's got too many things running on my laptop. So we're going to be running cells in these Jupyter notebooks. And just to show you, this is very zoomed in. Sorry. So depending on the software you're using, you will basically put your mouse in the cell that you want to run, and you will press this run button if you're in that Jupyter Lab or Jupyter notebook environment. You can also do this if you're on Windows using Shift Enter on your keypad, or if you're on Mac, it is Command Enter. Matt, you're muted.
Yeah, command return is the same as shift.
Command return. Okay, so I'm going to be doing that. So yeah, that would just be up here. You've then got a few other things that you should know about. So up here where it says kernel, you have the option to restart your kernel. That's generally a good thing to do once you have a crash, for example. You also have the output to restart your kernel and clear all of the cells, and then a final option to restart your kernel and run all the cells. So that will go through and run them all. That can be very helpful when you're doing long melts calculations. You can just run them and go away and do something else. Today we're going to be running them one at a time because the calculations we're doing are actually a little bit slow, and I want you to do some other things first. And if you're run them all, you won't be able to do those other things. Okay, so let's scroll to the top. So hopefully everyone has this activity one notebook open somewhere. If you do, can you put a thumbs up next to your self in Zoom as a reaction? If you don't, can you put a thumbs down just so we know how people are doing? It's obviously a little bit hard with online. So Keith, you have your hand up. Do you have a question? Or are you
I no, it's only because I don't know how to do a thumbs up. I'm good.
That's
Sorry.
fine. Okay. And remember, folks, if you haven't, please put a thumbs down. Don't be shy. We need to know if people are getting behind because otherwise they won't be able to catch up with this. So,
And also use the Discord. Whilst Penny's going through this, I'm monitoring the Discord chat. So if there are issues, post them there. If someone's completely stuck and we can't solve it just by a simple text response, there are a couple of voice channels on Discord. So if you're getting stuck and on the ask for help thing, and I might just say jump on voice chat and let's try and sort this out, and then we'll do that. Make sure you're muted on Zoom if we jump on voice chat on Discord is the only thing, but otherwise, yes.
okay.
I think
So the first thing,
saw no thumbs down.
yeah, no thumbs down. If people don't know, Matt, because I've lost my thing, do you want to just explain on Zoom how you do the reactions? Because I've now lost them on my screen.
I mean that assumes I know how to do it. 1 second. Oh yeah, there's a react button at the
Right,
bottom,
yeah.
and then there's a various options, thumbs up. You can do a rocket if you want, but yeah, there's a
No, we'll do
react
thumbs
button at
up
the
and
bottom.
thumbs down. Okay, okay. So the first thing we're going to do is run this first cell. This is just going to import your four main Python packages. So NumPy is used for your math and your stats. Pandas is used for handling data in a spreadsheet-like way. Matplotlib is probably the main plotting package that you're going to use. And then we're also going to import Seaborn, which is a different plotting package. So you're just going to do your Shift Enter or your Run button if you're using Jupyter. Then the next thing you're going to need to do is upgrade PetThermoTools. This is because Matt and I have been working very hard over the last 3 days trying to get everything to work perfectly for this workshop. So even if you've already installed it, this is just going to upgrade to the latest version. So you're just going to run that. And what you should get is you should get this message. Basically, I already have it, so that's why it says it's already satisfied. But then it will tell you, note, you may need to restart the kernel to use your updated packages. So we are going to do that. So here on VS Code, I'm going to press this restart kernel button. If you are on your Jupyter lab, that will be under this kernel and then restart kernel. So that's just necessary to do every time you basically upgrade a Python package.
It went by very fast, but for the total Python newbies, you can see that Penny deleted the number sign, the hashtag at the beginning of that pip install line to uncomment it before executing it.
Thank you, Paul. Yes, I should have said that. For those of you who are on MATLAB, this might not be super familiar to you. In Python, when you put that hash sign, it is a commented out line. It is not going to run. So once you've run it, you're going to want to comment it out because otherwise it'll run every time and we don't need to do this pip install upgrade every time. So in general, when things are green, they're not going to run. Once they go white or colored, they are going to run. Thank you so much, Paul, for pointing that out. Okay, so then we're going to run that first thing again. We're going to comment out that pip install upgrade PetThermoTools. So now it is not going to run. And then this is the bit that's going to be a little bit variable depending on how you installed Melt. So if you ran Matt's code, Matt, they can just comment out these two lines, right? Or it's not
Yes,
going to
so
matter. Yeah.
if you ran when you ran the install alpha melts function, it should have printed a message. Either it would have said alpha melt successfully added to Python path, or it would have given you a message similar to what's being shown here, something about import sys and sys.path append. If you got the message about import sys, sys.path append, you need to keep in these two lines, the import sys, sys.path append line, but then you need to change the file location here. You basically need to change this file location to be wherever the meltsdynamic.py file is on your machine. And that will be a file that was downloaded during that install alpha melts function. So you need to locate that on your computer and then point Python towards it in this line here. For the majority of people, that probably isn't going to be necessary. If you run import PetThermoTools as PTT, it should say whether or not it found the Python files correctly.
So if you did run Matt's thing that did it properly, you can basically just comment out these two lines. Sorry, that's not the hash. And then you will not need to run them. So basically, unless it didn't work, comment out those two lines, and then you're just going to run these two things by pressing run in that cell. This is basically importing PetThermoTools as PTT. So that means anytime we're using a PetThermoTools function, it's going to be called PTT dot. And then the most important thing is that it prints this version, and this should say 0.3.15. So that is the version I want all of you to be on. If you are not on that version, even if you ran this pip install, you probably just need to restart your kernel. So make sure that you do that step. Okay, if people are on 3.15, can we thumbs up on the reactions? If people have not got to this step, please thumbs down so that we don't lose you.
Donna said, can we slow down for a minute? So I think just hold it there,
Yeah,
maybe
we can
Penny,
just hold
and
it
we'll just
here.
give it
And yeah, if
everyone a
people
couple of
just
minutes.
put your thumbs down until you've had a chance to do this, then we know to wait for you.
Can I quickly share my screen, Penny, just to
Yeah,
show
go for it.
people the alternative? 1 second. And now lost Zoom. So yeah, what I was talking about earlier is if the installation process worked completely, and this basically means if you have admin privileges, even regardless of whether or not you put this 2 lines here or whether you comment them out, if the Python file, the alpha melts files are on your Python path permanently, you'll get this message here. If you don't get that message there, that's when you have to make sure you're using these 2 lines and you're putting in the correct location of the alpha melts for Python files. Wherever they are stored on your machine, you need to locate them and basically point Python towards that location using that line. Otherwise, it doesn't know where to go to actually look for the melts C library in order to run the calculations. But yeah, so hopefully for most people, when you import PetThermoTools, you'll get this message. And that's kind of like ideal. That means that we already know what alpha melts is. We're good to run calculations.
Okay. Okay, I don't see any thumbs down. I think Dawn is just retrying. Okay, the next cell is this one. So this is basically if you're Matt, do you want to explain this as a Mac person?
Okay, so when the melts calculations run, Paul mentioned that years ago you used to be able to watch every single step of the algorithm being printed. Those messages are still printed as the melts algorithms run. For some reasons I can't quite work out, and despite mine and Paula's best efforts, we haven't seemed to be able to sort this out. But essentially on Windows, all these prints happen in the background, you never see them. On Mac and Linux, it prints every message within the Jupyter notebook. And you can imagine that algorithm that Paul talked about, looping back through, checking phase saturation, dropping phases, adding phases, doing that for every step of a crystallization or decompression model, it ends up producing a huge amount of output text. And on Macs, this happens within the notebook itself. This cell here basically suppresses that output. This does come with some downsides, which we can talk about in a little bit, but it basically means that your notebook doesn't just get completely overwhelmed by these huge number of text outputs from the melts calculations themselves. In Mac, I don't have a good reason as to why this is the case. You need to run that cell twice. If you run that cell twice, if you're on a Mac, it will suppress those outputs and basically will mean that your notebook remains readable. You don't end up with just this huge list that seems to go on forever of melts outputs. It's something I'm actively working on trying to fix and solve because, as I said, there are a couple of downsides to doing this for Mac users, but at the moment it's kind of the best workaround that we have.
Okay, fab. And it seems like the people who are struggling on Discord have got it sorted. So basically, if you're on Mac, you're going to run this cell twice. So you go in it, you press run, and then you go in it and you press run again. If you're on Windows, this platform system Darwin is Mac. So you're basically not going to enter this loop. So it doesn't matter if you run this or not. It's not really doing anything. Okay, so the next thing we have to really understand to be able to use Python is the different types of data. So when we talk about strings, these are things like letters and words. So in the case of PetThermoTools, the most common strings that you're going to be working with are the names of the models. So that'll be things like specifying that the model you want to use is pmelts, or that the model you want to use is melts version 1.2.0, for example. We're then going to be working a lot with data frames. This is using that Python package pandas. A data frame can be thought of as a lot like an Excel spreadsheet, like a single sheet in a spreadsheet. There are columns, and these columns have data within them. That data can be a mix of what Python calls integers. These are your whole numbers, like 3. It then is other things called floats. This is 3.0, for example. So there is a slight distinction in Python between a 3 and a 3.0. Other things like 3.1 would also be a float. And then you will also likely have some strings within your spreadsheet as well. So that would be things like your volcano names, for example. Then within that data frame, if you think about a single column, in pandas, that would be called a pandas series. So it's a single column of the data frame, much like one column in your Excel spreadsheet. The biggest structure of data that we're going to be working with over the next few days are dictionaries. These are ways to put together lots of different types of data with keys, okay? So if you imagine, again, your typical Excel spreadsheet, you might have sheet 1, sheet 2, sheet 3, and sheet 4. In a dictionary, they would be your keys. So sheet 1 would be a key, sheet 2 would be a key. And within that dictionary, you could store 4 of these data frames, for example. So it's just a nice way to be able to return multiple data frames. Okay, so we're going to be working with these different types of data. So the first thing we're going to do is we're going to make a new variable called melt inclusion all. And we're going to use the pandas function. We know this is a pandas function because it says pd dot, and we loaded in pandas at the top as pd up here. So pd.readExcel, what this does is you give it the name of the Excel spreadsheet that you want to load in, and you give it the name of the sheet. So in this case, the data we're looking for is in the sheet name data. This could also be sheet 1, for example, or whatever it is. Okay, what we're then going to do is we're going to fill nans, so we're going to fill missing numbers with 0. And then we're going to inspect what this data frame looks like using this .head function. That is going to print the first 5 rows of your data frame. I would always encourage you to print your data frames if they've read in funny for whatever reason. This commonly happens in patrology when you grab your supplement from JPET and they have like the first row of the spreadsheet is just like the DOI or something to do with the authors. It will not read in properly. So just always make sure you inspect your data frames. So we're going to run that cell. And then the only final thing I've done here is I've asked it to print what the type is. So if you're ever in doubt about what data structure you're working with, perhaps you want to ask for help from ChatGPT or a friend, if you just type the word type and then put the variable name, here it's melt inclusion all in parentheses, it will tell you that this is a pandas data frame. So now you know what you're working with. Okay, so within the data frame, we're going to practice accessing some of the columns. So what you're going to do is so if you got the name, thanks Suda Barry, name PD is not defined, that is because you probably didn't run this cell at the top again. So go through, run this cell. Christina, if you have not found your file, it needs to be in the same folder as this activity. So if you downloaded them from GitHub, you probably need to go and grab this Excel file and dump it in the same folder as your notebook. Okay, so to extract a column, what we are going to do is we're going to type the name of the data frame, melt inclusion all, and then we're going to use our big square brackets and our quote marks. And then you're going to put the name of the column that you want inside this. So for example, if we want to pull out the SiO2 liquid column, we would type melt inclusion all, big square brackets, quote marks, SiO2 liquid. That is going to give you what we call a pandas series. Remember, that is one column within the data frame. If you're in doubt as to what data type you've made, you can simply type the word type and the thing that you copied from above, and it will tell you it's a pandas series, so you know what you're working with. Okay, so everyone just have a quick go. I want you to try extracting the FEOT_liquid column just to inspect your liquids, and then you're going to put a thumbs up in the chat once you've done that. And please do these reactions. It's really hard to do workshops on Zoom unless we know whether people are caught up. Do not be embarrassed to put a thumbs down. Okay, so we've got a couple of thumbs down. If you have put a thumbs down, if you could type in the Discord day one, ask for help, what stage you're at or what the problem is, we can help you, and you could even share your screen because you're probably not the only one struggling. So Sue, what's happening for you? Do you want to unmute and explain?
Yeah, I did run the import pandas as PD, but for some reason I'm still having trouble. So I'm starting from the beginning. I just need a little more time to see.
Okay, we'll just give people a little more time then. If you want, if you're still struggling in a minute, we can share your screen. I'm sure you're not the only one who's having the issue, and it will be helpful for people to see.
Thank you.
So anyone else having trouble, please post in the ask for help. You can send a screenshot of what's happening, or if you just need some more time, just type, I need some more time. We don't want to lose anyone at this step. Christina, you need help. Do you want to, hold on, let's have a look. No module open PYXL. Okay, in general, so I'm actually going to share my screen because share this message. Hopefully everyone can see this. In general, in Python, if you ever get this import error, missing optional dependency or anything, or like missing package, it tells you to pip or conda install openpyxl. If you ever see anything like that, you have two options. You can either open up your Anaconda prompt and you could type conda install and then whatever is asking you to install, that is the like technically better way to install things. Otherwise, in your Jupyter notebook itself, you can simply make a new cell and go pip install and then whatever the name of the package is that it's telling you you're missing. So you will commonly encounter this, particularly if you've not used Python much, where you will come across a package that you don't have yet and then you can install it this way. Hopefully that makes sense. Where else are people caught up on? Let's see, chats. Okay, so a few people are having that PD is not defined error. So that is very indicative that you did not run this first cell. So if you go back and you try and run this first cell, this is because you haven't imported pandas. So it doesn't know that you want to use pandas of all the packages in the universe. So you absolutely have to run this first cell. It's really easy to miss this when you've done that pip install upgrade and then gone back and restarted your kernel. So if folks who are getting that PD is not defined error could go back and run that first cell, that would be great. And then if you posted in the Discord, if you could like as in post, oh, it works now if it works, and otherwise if it not works. Okay, Lycan, are you still having issues? Okay, another error, see above. Just a little thing with pasting errors. The most important information in an error message in Python is actually at the bottom. So make sure when you screenshot your errors, you screenshot from the bottom upwards, because the bottom is generally the thing that tells us the most problematic thing that's happening. So Sue, if you could screenshot the very bottom of that error, that would be fab. Okay, so just to show you guys why that's what I want, if I pull over this, let me show you what the top of Sue's error says. So it basically says there's an error with this line, PD read Excel, but I'm not sure exactly what the problem is. And then the moment you have the bottom of that, you see that the issue is right at the bottom, no such file or directory found. So what that tells me is that that file is not in the same folder as the notebook we're running it in. So again, just go to your file explorer, whether you're on Windows and Mac, make sure that the notebook and the thing are in the same folder, and then you can go from there. If you don't want to put them in the same folder, you can use relative path. So you can put a wee little R here, and then you could have a longer path like this. So you would basically paste in everything, and that would allow you to point towards an Excel spreadsheet that is somewhere else. I'll just paste this into the Discord so that you'll have it as a reference. But for this workshop, it's just going to be easier if you just make sure that it's in.
Okay, working on it. Thanks, Penny.
Yeah, no worries. Again, we really don't want to lose people, so we planned lots of time for this. Other people, Christina, do you want to share your screen? Otherwise, you can hop on with Matt and on a voice chat, and he can maybe help you.
I don't know how to use the voice chat.
Okay. If you just share your screen, it's probably something that's useful for everyone to learn, because we're all going to be helping students with this. So.
Okay. Can you see my screen?
Yeah, I can see your screen. So if you scroll up to the top.
Okay.
And then that first cell, can you just put your cursor in it and run it again?
Okay.
And then run it with the play button. So go to the, I'm not sure exactly what you did, sorry. Did you run that with Shift Enter? Or, so the cell above that says import NumPy, just press the play button for me. Yeah, so click in that. So you need to click in the cell above. So you need to put your mouse in the import NumPy as NP cell.
Wait, what did you say?
Click in there so it gets selected.
Click on what?
Click in that cell. So put your mouse in that cell, because do you see currently it's currently highlighting cell 4, so you're not in the right cell. So you need to go up to where it says import NumPy as NP, and you need to put your mouse in there and click. There we go. And now press the play button at the top.
Okay.
Okay, and now press the play button again.
Okay.
And now press the play button again. Okay, so what's happened here is you're still on the wrong version of PetThermoTools. So you need to scroll up. So go up to the second cell down. Do you see this one, cell number 6? If you put your mouse in there and delete away the hash button, do you see there's the hash?
This one?
The next one down. So go one down. There you go, delete that.
Okay.
Okay, and now press the run button.
Okay.
The play button, yeah, that one. Okay, so that's now doing your... Okay, scroll down. Let's just check it went through. So you can see now you've successfully installed 3.1.15, so that's what you want. So now scroll back up to the top and go kernel. So at the top, do you see it says kernel? Like where the play button is, just to the right of the play button.
Oh, yeah, okay.
Yeah, kernel, and then say restart kernel. And then say restart. Fabulous. And now scroll up to the top. Put your mouse in the import NumPy as NP thing again. So click in it. And then press play. You're then going to put that hash back. So you deleted away that hash in front of the pip install. Okay, and now run that as well. And then run this. So now you're on 3.15, so now this is right. And then you're on Windows, right? So you can just run this and move on. So press the run button.
Okay.
And then keep pressing run. Keep pressing.
Okay.
Hopefully we're going to get there. Run now.
Ah,
Scroll down. Okay, so now you don't have the file in the right folder, so that's what you need to do. You need to now make sure that you've downloaded that Excel file, put it in the same folder as this notebook, and then you should be good just to run this cell again, and then you will be all caught up. Does that make sense?
okay, thank you.
So yeah, download the Excel file, put it in the same folder. Okay, yeah, if you stop sharing and if you can't work that out, you can hop on with Matt in a minute, or you can hop in a breakout room. Okay, I'm gonna assume that we are good to move on. Matt is gonna open up a breakout room, so if anyone is still lost, you can go in there. Just so I can check, can you all see where it says melt inclusion SiO2 underscore liquid? Am I sharing the right screen now? Because I've got a lot of things on my screen.
Yes.
Thank you. Okay, so just what I asked you all to do was to extract the FEOT column. So you would simply type FEOT. The other thing you can do is copy and paste is very much your friend in Python. So you can just copy and paste and put it over here. So that would extract you out the iron contents from your data frame, for example. Another thing we might want to do is we might want to summarize what content is actually in our data frame. So this is a spreadsheet from Dan Rasmussen's supplement of different arc volcanoes. We might want to know what different volcanoes are. Okay, sweet, we're recording again. Okay, so what you could do is you could just type volcano into the like we did, but then you can see you can't actually see all 3,466 values. So we can use this really useful thing called unique. What that will tell you is it will tell you all the unique values in that data frame. So you can see that the first 5 values are all aggregate. It's just going to say that once because there's only, one unique value of that. So we can run that. And what that will then give us is a list of all of the different volcanoes that are within this. So that's useful so you know approximately what data that you have. Okay, so the other thing we can do with data frames that's going to be really, really helpful for petrology is we can filter them, okay? So we might want to only take samples where our silica content is less than 52, for example, if we're worried about like crustal contamination, for example. So how you would do that is to start with, you're going to make a statement that is either true or false. So in this case, I might want to say that the silica content is less than 52. So if we type mi all si underscore liquid less than 52, what that is going to do is it is going to print a list of true and false statements. Okay, so you can see for the first row, which is row 0 in Python, this is true. If we do greater than 52, or let's say greater than 60, we can see that that is false for all of these. So this is a list of true and falses. And what you can then do is you can apply this list of true and falses to your data frame. So if you take your true and false statement, we're just going to call this, let's call this filter. What we can then do is we can give our original data frame, we can put this filter within brackets. And what it's basically going to do is only take the columns where this is true. So what we see, oh, sorry, it's capital F. What we see is that of our original 3,000 rows, we have 1,568 rows where silica is more than 52. So Megan's getting up. Megan, I think you might have typed a 0. So it's really important with Python that I would always recommend you actually just copying the column names and pasting them in because it's the best way to tell apart like characters which aren't obvious, like an L or a 1 or a 0 and an O. So if you're in doubt, okay. Yeah, Heather, when you guys are struggling, please post a screenshot of your code. Like from Megan, it made it super easy for me to diagnose what's going on there. Okay, so that would be one filter where say we want our silica content less than 52 because we're worried about crustal contamination. We might then want a second filter where we consider the MgO content. So maybe we also want the MgO content of the liquid to be more than 9 weight percent. What we can then do is we can combine these different filters. So we want both of these to be true. So we would say filter and filter 2. And that would then give us a list of only 138 rows that have a silica less than 52 and an MgO greater than 9. So Anton, what has happened there is you have not put filter equals. So the variable filter is not defined. So if you, in Python, if you just do something like this, it's just a list of true and falses, but this doesn't have a variable name. What makes it have a variable name is when I type filter equals it, and then suddenly it is something called filter O. Heather, you can just take a photo with your phone, no? We can deal with, for those on government computers, we can deal with pictures taken of screens. Okay, so you need to define those. You don't actually have to define it like this. What you could also do is you could just put these filtering statements within parentheses inside these square brackets, and that would also work. Let's see what Heather's done wrong. Fortunately, with the government. Heather, could you take a picture of the top bit as well so we know what you typed? Where else are people getting stuck? Alex and Sarah. So for those of you who don't know,
Penny,
Alex.
can you?
Yeah, Matt, what were you going to say?
I would say I'm keeping track of the Discord, and so Heather, what you've managed to do, Heather, is you said melting, you've done a melting conclusion all data frame, and then in the square brackets you put volcano. Volcano is just a list of volcanoes, so it's a string. What Penny showed and what we've been trying to do is using the chemical compositions, so like the silica underscore liquid, which is then a array of numbers. And so the reason why it's giving you that error is because you're saying less than 52, but it's just a series of names. It's a string variable. So when doing this, we've got to make sure that what's in the square bracket, so instead of volcano, it should be SiO2 underscore lick, and then it will work. Because at the moment you're trying to say less than 52, but it's all string variables, not numbers in that array there.
Okay, so I really don't want to lose people at this step. So I have 2 fabulous grad students who are on this call, Alex and Sarah. They are both Python experts. So what they're going to do, Alex and Sarah, if you don't mind, would you mind, or Matt, open a breakout room and Alex and Sarah can hop into one each? People that are getting stuck at this step, please ask for help. We're going to lose you if we've lost you at this step. And then hop in there if you're getting stuck, and then come back in a few minutes once they've been able to help you. Does that work, Matt? And thanks, Alex.
Yes, so there are 2 breakout rooms. So if Sarah, you don't mind popping in one, if Alex don't mind popping in the other,
yeah, sounds
that'd be
good.
great. So yeah, I can't
Thanks.
seemingly go to breakout rooms without killing our recording.
Okay, and yeah, if people are getting stuck with this, keep posting your things in the ask for help, hop in those breakout rooms just so we know to wait up.
I am also on the voice chat on Discord, so you can come into the Discord chat. There's a help voice
But
chat
they
on
can't
Discord.
share screens, can they,
They
Matt?
can share screens on that, so you can
Okay.
use anyone that obviously I realize the people with the government computers this isn't helpful, but anyone else can come onto Discord and share your screens on there as well.
Matt, can you see how many people we have in breakout rooms? Oh, no, hold on.
At the moment, Susan is in a breakout room, and that's it.
Okay, well, we'll just give her a minute to get up to speed. You ran, let's see what's happened here.
Dawn, you have your hand up.
Melting fusion, all less than 52, more than 9. Interesting. Dawn, hit us up. What's up? Oh, okay. I'll solve this problem first, actually. Jay Wathaker, What's happened here is your parentheses are not correct. So if you want to put I'll actually just share this so that everyone can see, because this is a really common, hopefully I'm still sharing. So this basically what has happened here is the first thing, mi all SiO2 underscore liquid less than 52 is wrapped in parentheses, but the second thing is not mi all MgO lick greater than 9. So when you're like putting these true and false statements together, make sure you wrap both of them in parentheses before you have that and sign. So if you could give that a go and see if that fixes it, and then just post if that fixes it, that would be great. Dawn, do you want to go now?
Yeah, I just want to point out that your code doesn't have the parentheses around the second part. So I think that's where people are coming up.
Yeah, okay, that's so weird, but when it works, yeah, okay. Yes, my bad. Thank you, Dawn. Does that fix it for people though? That might not be the problem. Let me know if that didn't work. Those who that works for you. Yeah, so I don't know if this is just different versions of pandas, like you get away with sloppy coding. Maybe Sarah has an insight into why that worked for me and not for them. But yes, you should always get into the habit of wrapping with parentheses. Okay, I assume Sue is still. Let's see if anyone else is struggling. I'm still stuck. Christina, could you hop into one of the breakout rooms? I'm pretty sure your file is not in the folder, although I haven't got the bottom of the error message. If you hop in breakout room 1, they can help you. So I'm just going to take a second just to, again, show you a little bit about these error messages, just because you are going to be sending us lots of questions over the next few years. And so when this cell runs properly, you can see it prints the type and it prints the data frame. If I then put something wrong, like data 1, it's not going to find it. So basically the error message, the first thing it tells you is which line the problem is on. And then it also tells you this very bottom bit of the error is the most useful. So ideally you would send a screenshot of the code, the top and the bottom, but if nothing else, the bottom and the code. This bit in the middle you can often bypass, but it's just, yeah, frustrating that you can't put all of the error messages in a single screenshot, but just so you understand the hierarchy. Okay. So what we're going to do is when we actually look at this data frame, you'll see that there's quite a few values where the water content and the CO2 content is 0. So for those of you who have done melt inclusion work, it's quite obvious how this comes about. This is possibly because your like ion probe had a contamination signal for carbon, so you deleted that point for carbon. Maybe you measured it by FTIR and one was below the detection limit. So if we want to be calculating pressures, we don't really trust the values where water or CO2 is 0 because that's very unlikely. These natural magmas are in equilibrium with mixed fluids. So for this data set, we're just going to set up 2 different filters. We're going to set up a H2O filter where we specify that the column H2O is greater than 0, and a CO2 filter where we set up that CO2 is greater than 0. And then we're just going to concat them together. And we're going to make a new data frame called melt inclusion underscore filter. And it's going to be melt inclusion all, and then these 2 filters applied together. So we're just going to run that cell. And if you're ever curious, like how much you've ended up filtering out, you can use the parameter len. So if we see what the length of the original data frame is, we see that it's 3,467. And if we want to see how long the filtered data frame is, we can see it is, 1230. So we've lost a significant number of our melt inclusions simply because they didn't have both volatile contents having been measured. So the next thing we might want to do is say for your PhD or your postdoc, you're only interested in certain volcanoes. So you can see there's volcanoes here from a range of countries. We have some in Chile, we have some in Mexico, we have some in the Aleutians. We might want to filter out a specific volcano. So how we're going to do that is, again, similarly to these filtering steps we've done so far. And just to say there are a variety of ways you can filter in Python. What we did before is we had the data frame name and then a square parentheses with the filter inside. You can also use this .lock notation. It does the same thing, so don't worry about which you use. So in this case, what we're going to do is we're going to filter our data frame for where the volcano equals Augustine. Okay, say we're only interested in Augustine melt inclusions, we can set up that filter. So we'll run that. And again, this head symbol is printing the first 5 rows, but you might want to print all rows, and you can see that there are 29 melt inclusions from Augustine. So what I want you to do is I want you to copy this code into a new cell underneath. I've left you one here. And you're going to do the same, but now you're going to try and get the melt inclusions where the volcano is Okmok. So you're going to want to define a new variable name. So it's not going to be called Augustine anymore. It's going to be called Okmok. And then you're going to have to adjust this filter so that instead of Augustine, it reads Okmok. So have a go at that. And again, if you could actually, raise your hand when you're done, because that sticks around longer than thumbs up. And if you're stuck, we're not going to call on you if you've got your hand raised, post in the Discord and we'll call on you to unmute. So yeah, if everyone could have a go at that, making a filter for Okmok instead.
The other thing you can do once you're done is you can take a screenshot or a photo of your successful printed Okmok thing and post it in the Post Your Answers channel on Discord. And hopefully we'll get a few, that'll keep a track of that as well.
So yeah, have a go. What I would do, honestly, is I would just copy the whole thing, paste it down below, and then edit it. Copying and pasting is not something to be ashamed of when you're doing Python coding. You should be using your Control-C, Control-V all day. Okay.
And just reminding everyone that the 2 breakout rooms plus I'm on the voice chat and Discord if there are issues.
Is there anyone in the breakout rooms, Matt, or should we call Alex and Sarah back and we can just spawn a breakout?
They have one each.
Okay, perfect. Okay, I'm assuming no one's having any issues because no one's posting, but I'll give you guys a minute longer and then we'll go from there. Okay. I think Liam's actually about typing something. Let's see if he needs help and then we'll move on. Can someone remind me how to display more than 5 rows again? Great question. Thank you, Liam. So just a reminder, .head shows you the first 5 rows. .tail shows you the final 5 rows, which can be helpful. And if you just delete this entirely, you get all of the rows. You won't get all of the rows if it's a massive data frame. Pandas will like truncate after a certain number. Just for those of you who aren't used to Python, MATLAB automatically prints, as I'm sure many of you know. Python does not print. So if I remove this final thing, it won't show me anything. So in general, if you want to inspect the thing that you've just made, you have to type its name again at the bottom. That will print it when it's on its own. The other thing you can do is you can do things like print, and that will print it even if it's not the last thing, because by default, Python will only print the last variable that it shows up. Okay, so we've done that for Okmok. Hopefully it'll look something like this. And then we're also going to do the same thing for Shishaldin as well. So you'll find these below, but this would be, again, how you'd filter. So now we have 3 volcanoes that we've pulled out from the Aleutians. Now, what we might want to do is we might want to combine these all together into a single data frame that's called Aleutians. Perhaps we're only interested in these 3 volcanoes. Perhaps we'd want to add in more Aleutian volcanoes if they were there. So to do that, we're going to use this PD concat function. This is basically a way of joining data frames end on end. So what it's basically going to do is it's going to take all of the columns. If there were different columns, it would try and fit the data from each individual data frame into those columns. If, for example, the Okmok data frame didn't have a calcium liquid column, but the others did, it would just fill those columns with NAND. But this basically gets all the data into a single data frame that we're going to call Aleutians. And again, it hasn't printed anything, but if we wanted to print it, we would just type the variable name. And there we go. We have Augustine, Shishaldin, and Okmok will be sandwiched in the middle. Again, Python hasn't shown all of the rows because it's decided that there's too many of them. Okay, so to start with, we might want to look at the data that we are plotting. So we can use this basic plt.plot function. This is going to be the quickest way to make a very, very basic plot. And it might be that we want to look, say, for just Shishaldin at what the MGO content versus the FEOT content looks like. So again, we're going to basically make these panda series. So we're going to make that data frame and its column within square parentheses. And we're going to plot it for MGO versus FEOT. What this does here is this determines the symbol. So right now it's plotting a circle. That's what the O means. And the K gives it a black outline. We're then going to specify the marker face color. That is the MFC. This is Y, which is one of the default Python colors. It's this horrible yellow color. And then we're going to also give the data a label so that we know this is Shishaldin. So you can run that. You could change this. Say you would rather have a diamond and say you want it to be red because you don't like this gross yellow. You would change this to, I just deleted it. You would change this to a hat and then you could run this like this. Now you might say, well, some things are missing from my plot, and you'd be absolutely right. So we're going to want to add an X label. So plot X label MGO liquid, and then we're going to want to add a Y label. So plot Y label SiO2 liquid like that, and that will add your labels. And then you might also want to add a legend. And again, I'll paste this into the... Does Python just plot from the most recently accessed data frame? Great question. No, it is plotting from whatever data frame I display here. So you can see this data frame is called Shishaldin. So it's plotting from Shishaldin, and then it's grabbing the column MGO liquid. I could also do this from Aleutians. So I could come down and I could make a plot that's showing all of the Aleutian data as a single color now, and you would see it like that. Now that's not particularly useful because we want to know, and this label would then be wrong. This would have to be changed to Aleutians. That's not particularly useful because we want to know what the different volcanoes look like. So what I'm going to ask you all to do now is take this plot, which you should all have, and you're now going to add on Okmok and what's the other one? Augustine onto this as different colors and symbols. Once you've made your plot with 3 volcanoes on, actually, I labeled this wrong. This is FEOT, not silica. Once you've made this with all of your volcanoes on, paste it in the post your answers chat so that we can see how people are getting on, and we'll see what horrible color schemes people have chosen for their plots. Have a go at editing that. Again, what I would probably do is just copy this line and replace Shishaldin with the name of the other data frame, and then choose the symbol and color. And I'm going to paste in the Discord some options you have for symbols and colors quickly.
Yeah, so Penny, I just think this is going to be a good point to pause for 5 to 10 minutes or so and let everyone catch up.
Let's isolate what's happened here. Melt inclusion filled. Did you run the person just posted Anna C? Did you run the cell above? So in general, folks, just so you all know, let me just pull this over so you can see how we're diagnosing these bugs. In Jupyter, you get this little number by the side. So this tells you that this was the 21st thing to have been run. If you haven't run a cell, it will just be a set of parentheses without a number in it. So in general, if it ever says something isn't defined, go back to the cell where that thing is defined, which in this case is the cell above, and check whether a number appears or not. Hopefully that. And folks, if you can post your answers in the answer thing, that will just allow us to keep the help thing for people that are stuck. Anna, did that, if that fixed your problem, could you post that it worked? Okay, so yeah, get posting your pretty plots, folks, once you've done them. And if everyone can put their hand down from the last thing, just so we can keep track of how caught up people are and how behind we've got. Nice plot, Heather. If you've made that plot, try plotting silica on the x-axis versus sodium on the y-axis. So by editing those names for the columns, and again, you can post your picture once you've done. It's amazing how many people have chosen the same color scheme. And for those of you who know Python really well, I know this is a little bit slow, but the idea is once we can get everyone running cells properly, we'll be able to go through the rest of the workshop with less pauses. So you can read a paper in the background while we're doing this, but hopefully we can all be patient and then we can get going with the rest of the science for the rest of the workshop. What help do we have? Try to choose the ugliest colors. I like your colors, Ludmilla. Oh, hold on one second. Your legend is not printing. You've missed, Alex, you've missed the open parentheses, close parentheses on your legend. So it's plot.legend, open, close parentheses. I'm just pasting in to the help the different symbols that you're allowed to use in Python. So we're using O and diamond. You can also use things like P, that makes pentagon, star makes a star. And I'm also going to paste in a matplotlib color guide. Till you get really good at Python, it can really help to print out these things, put them above your desk, and then you can make as many plots as you like.
Well, that was an unusual one.
That is weird. Lynn, can you try just uncommenting the plot.x label, see if that really is the problem? Because that is a very odd error. Unless Sarah has any insights here.
Yeah, it works great if I just run it with the legend, but and I mean I'm not going to hold things up. I've used matplotlib a lot, so
okay, that is just such a weird error. I don't know. Maybe one of your.
I don't see a typo.
No, neither do I. Let's see. Ooh, yeah, you know what you're doing. You know how to run a Jupyter notebook.
And I know how difficult matplotlib can be, but this is a new one.
I'm going to ask ChatGPT what it thinks about this. And folks, yeah, this is a really good point. AI, although questionable in many reasons, is going to help you so much with coding. Like if you're really stuck, you can just paste the whole error messages in, paste a screenshot. It will give you a tremendous amount of help. It's very exciting in that it's definitely lowered the activation energy. So it says earlier you must have like you've overwritten plot.xlabel somehow, Lynn. So I think you do have to restart your kernel and go again.
Yeah, I've run it too many times. Thank you.
Interesting. That's an odd one. Let me just finish posting in the Matplotlib color guide, and then we can move on to the actual melt calculations, which is why you're all here. Matplotlib. Seems like people have. Okay, copy image.
Yeah, now it's happy.
Okay. Yeah, Python can be a pain in the ass, folks. Don't take it personally when it happens. Okay, so I'm just going to quickly show you, I've just uploaded a thing of all the official colors. So there are a few colors which you can do with just like R is red, K is black. There's also this list of colors. So you can be really fancy and you can say you want the color to be dark golden rod, and it will plot it as dark golden rod. There are other ways to make colors in Python, but again, as a first start, printing this out on your desk as you get started using it is good. Let's see how many people we've got posting things. Okay, it seems like we've got lots of plots, which is what we want to see. Okay, so I'm just going to talk you through another way to make plots, because Matplotlib, as Lynn said, is very diverse and annoying in many ways. So that is a single plot, but as we know as petrologists, we often want to make 2 plots or maybe 3 plots. And the way we would do that would be using subplots. There are a variety of ways to make subplots in Python. Matt and I actually do them in different ways. What this is basically doing is it is saying I want a subplot where I have 1 row and 2 columns. So that's going to make a side-by-side plot. You can then specify the figure size. So we want, in this case, this would be 10 inches by 4 inches down. And then AX is basically now has 2 parts to it. So we're going to call the first part of A, this is using 0 because again, Python starts counting from 0, whereas other languages start at 1. So basically your A0 replaces what you had up here as plt.plot. So you now have the axes that you want to plot on and the thing that you're plotting. So this would be very similar to the code that you've made. The only thing to realize is that as you swap from plot.plot notation to this subplot notation, you can no longer use this .x label. You have to use .set_x label. So again, it's just like a weird oddity of Matplotlib. You'll get used to it. So this allows us to plot, for example, iron versus magnesium and potassium versus magnesium on the same plot. What I would recommend is all of those of you who are new to Python, take bits of code like this and make a notebook, like a Word document or a notes file of useful code. Once you have a subplot set up, you can just copy and paste it, and then you can just swap out your data frames, swap out your columns, but then you have the basic plotting structure ready to go, and then you just adapt it from there. So I have lots of like little snippets of code on my laptop that I use all the time because I can't be bothered to type things out from scratch. Okay, we're just going to quickly go through some other useful visualizations. So we can use this Seaborn package to make what we call violin plots. So this is a way of just looking at data. So the way this notation
Not right
works...
now, no.
Oh, are we good?
In a little bit. Yeah, I'll come find you.
Okay, I think someone needs to mute their mic, maybe. That's fine. So how this Seaborn notation works is you set up your figure. Again, this is 10 inches by 6 inches. And then you use this sns.violinplot function, and you're going to specify an x variable. This is basically going to split the data discretely along the x-axis. So you want this to be something that has unique values like volcano. You would not want to put this as silica content because that is a continuous variable. And then you're going to put your continuous variable on the y-axis. So in this case, this would be H2O liquid. So this would just allow us to visualize what the water distribution looks like in these 3 sets of melt inclusion samples. So you can run this and you can see that Augustine extends to much higher water content than Okmok and Shishaldin. So initially what we might guess is that based on the fact that we know the amount of water in CO2 increases with pressure, these might be higher pressure inclusions. Now, water is not the only variable that matters, so we can also look at CO2, for example. And we can see that similarly, Augustine actually extends to higher CO2 contents. We just want to adapt this. So just quickly change this to silica content, make a silica content violin and paste it in the post your answers, and then we'll move on to the actual calculation. So yeah, you can basically just set this variable for anything you want in your data frame. Have we got anyone who is stuck?
And if you are having issues, please don't hesitate to kind of reach out, let us know, post the message. We want to make sure that no one's falling behind. And we have plenty of time to get through what we have planned today, so we don't have to keep to a really strict schedule.
Yay, look at that. K Druby, that is beautiful. What you can see is that Augustine extends to slightly lower silica contents than the other volcanoes. If someone wants to make an MGO plot, that would be helpful as well, just so we can see. Yeah, so Lynn, very helpful. Thank you so much. And what you can do is once you start plotting histograms and violins in Python, it will print this annoying text. This gets more annoying when you're plotting histograms. You can just suppress that by putting a semicolon. Oh no, wait. That.
It's on the final line.
Oh
So
yeah,
your
it's on the
label.
final line. Sorry, my bad. So here, there. Yeah, then that will suppress it there. For the histograms, you do it on the line. Or if anyone made an MGO. Yes, so what we can see is there are actually quite low MGO melt inclusions, particularly for Shishaldin. Okay, so this is one way of visualizing data. A couple of things that we're doing with this violin that is important to recognize is this cut equals 0. What this means is it actually trims your violin at the point of the min and the maximum of your data. So if anyone's used things like kernel density estimates, you'll see that you often get that tail, which isn't represented by true data. If we get rid of this cut equals 0, what you'll see is that you get this misleading tail. So even though we know that the CO2 content can't be less than 0, you end up with these like anomalously low tails. And this can be really problematic when you're plotting things like pressure, because it makes it seem like you've got this tail extending down to high or low pressures when you really, really haven't. So I would advise always using this cut equals 0 parameter. The other thing you can do is the inner part of this violin plot. Currently what it's doing is it's showing a dot for each individual data point that you have. You can also change that to things like stick. And that will just draw a stick representing each data point. Okay, there are other ways we can visualize distributions of data. Another way that we really like in our group is called a jitter plot. So what this is basically from R. Anyone who knows R will be familiar with this kind of plot. So what it does is it plots a point for each individual measurement of water, and then it offsets them randomly in the X direction, just so that all the points don't plot on top of each other. So the X is meaningless. So again, this is the kind of code that you could just paste into a document and edit. So basically what we're doing is we're just specifying that there are 3 unique volcanoes. We're going to loop through those volcanoes within this for loop. So it's basically going to look for Y values, which is basically the rows of the data frame where the volcano equals the first volcano through the loop, and then the second volcano through the loop, the third volcano. It's going to grab the water content, and then we're just going to set up an X position. This basically determines how offset things are left and right on that jitter plot. And then we just plot the X and the Y positions. We're also plotting a star, which is showing the median data plus or minus the sigma data using an error bar. And that just gives you, again, a nice plot structure you can just adapt. Say you wanted your jitter to be a little bit more compressed, you would just change this X parameter here to be 0.3, and you can see they all condense down. So again, this is a useful way of visualizing distributions of data in non-traditional things. Okay, we've already done that. So what we're going to do now is we are finally, now we're all aware of Python, we're going to run our first saturation pressure calculation. This is basically, imagine you've measured a suite of melt inclusions, you have their major elements, you have their volatile contents and you want to calculate a pressure at which they were vapor saturated. And that is generally used as an insight into the storage pressure of these magmas. You can do this in VesiCal, and I do not want to say that this is going to replace VesiCal because it's not. This does not give you access to all of the different solubility models, which is the advantage of VesiCal. It's just so that you have this in the same ecosystem as this package so that you can use those pressures to go on and do other thermodynamic calculations. And that's what we're going to do here. The other thing that's a bit different is for VesiCal, you need to specify a temperature. What this code is doing is actually using melts to calculate a liquidus temperature that it's then trying to find the pressure of saturation at. So it's basically it's asking melts for the specified bulk composition that you have, what is the liquidus temperature, and then at that temperature, what is the pressure at which a vapor first appears. So what do we need to specify to use this? We need to specify the model that we want to use. So this is MELTS V1.2.0. That would be the only model I would really consider using for saturation pressures because it's the only one that has water and CO2 in and is, set up for this. That model is basically MagmaSat for those of you who think in VesiCal speak. You then need to specify your bulk composition. So this is your data frame of those elution magmas. You need to give the algorithm a first guess. Did you remember Paul had that flowchart of how MELTS works? One of the key things was an initial guess. So this would be your initial guess in Celsius of your liquidus temperature. You then need an initial guess in bars of your saturation pressure, so approximately where in the crust do you think these come from? And then you're going to specify the oxygen fugacity. This is important because the solubility model MagmaSat, which is what's MELTS V1.2.0, has different coefficients for Fe3 plus and Fe2 plus. So you need to basically decide what buffer you're at, or you could specify an Fe3, Fe total liquid content because the model is sensitive to that. So here we're going to run at FMQ plus 2. So you set that as a buffer name and then an offset, and that is going to be a positive offset. The final thing is this timeout parameter. We're going to run this because it can be slow. These are hundreds of calculations. And then Matt is going to explain a little bit more about what PetThermoTools is actually doing. Anyone who's run VesiCal or other melts will know that MELTS crashes. And in this data frame of saturation pressures we've asked you to calculate, we know that at least 2 of them are going to crash, okay? So this code is going to do something to deal with that. What you're going to do for now is just press run. We're going to leave it running, and then we're going to hand over to Matt, who is going to talk us through exactly what the code is doing to try and handle some of these breakages. And this is what really sets PetThermoTools apart from other ways of running MELTS calculations. Okay, Matt, over to you.
Okay. Thanks a lot, and well done, everyone. I know, especially if you're relatively new to Python, it's probably felt like quite a lot this morning. But overall, I think everyone seems like doing really well, and we're getting loads of people returning really nice results, very pretty graphs, and very interesting color choices, I will say. But otherwise, it's looking pretty good. So yeah, as I say, Penny says, hopefully everyone's hit run on that cell, and those calculations are running. And basically, whilst they're running, we're going to chat through kind of what's happening in the background, essentially, and also a little bit more about kind of why we developed PetThermoTools and what our initial intentions for developing PetThermoTools were as we did it. And so remarkably, it's actually got the correct screen on. I wasn't expecting that. So this has really been a collaborative effort from myself, Penny, Paula, and Paul. We're also very fortunate that back in August, we got a NSF Geoinformatics grant to help fund this work. And so this has funded quite a lot of the work I've been doing. It's going to help fund future workshops. It's going to help fund Paula and Paula's development in the underlying Alpha Melts and Alpha Melts for Python packages. And it's really important in terms of the kind of like long-term future of this package in terms of keeping things developing up to date with new chip sets, etc., and things like that. So yeah, just wanted to mention that quickly first. And really this package, PetThermoTools, started probably around 3 years ago. It was probably when I started working on it. It's taken many, many different forms since then. It only recently became more useful to people other than myself. But it has been quite a long, drawn-out bit of work in order to get to where we are now. And there's various reasons why I wanted to develop it, right? Firstly is, as Paul talked about earlier, there are many different reasons why you might want to use thermodynamic modeling. There are many different ways people have used MELTS algorithms in the literature to address a wide array of different kind of problems and questions in igneous spectrology and beyond that as well in even into kind of metamorphic spectrology and things such as this. Okay. And when we're kind of thinking about how you actually go about to run these calculations, as once again indicated earlier, there are many, many different options for how to do this. You might, in the past, some people here, and I know I did this, you might have used the original kind of Rhyolite Melts GUI. Now, in my master's work, I think I ran somewhere around 550 melts calculations, and I hand typed the composition for several different starting compositions, hand typed starting pressure, oxygen fugacity, water content for each and every one of those, and then ran them individually in the GUI. It was at that point I decided I was never going to do that again, and so started looking into what other options are there for trying to do this in a bit more efficient way. But having said that, the GUI can be useful, and Paula mentioned earlier the Easy Melts package as well. These can be really useful if you just want to have like a basic idea of your system. You have a composition, you want to know broadly what you would expect to see as it went down temperature, as it crystallized. Very easy to use, very accessible, but you kind of are slightly limited in what you can actually do with these tools, right? It's very easy to run one calculation. If you wanted to run 1,000, well, that's more problematic. At the other end of the scale, we have things like Enki. And as Paula mentioned earlier, this is really the kind of cutting edge of development in melts. If you can do a huge amount in Enki, you can model any system you can really imagine within igneous spectrology, and you can run really complex models. If you're a really confident coder, you can easily set up a system where that kind of those melts calculations are interacting with different parts of a system, like exchange of heat between different components, controlling your kind of the state of your system and the new equilibrium state. Having said that, using Enki isn't necessarily straightforward. I don't know many people that have gone on and said that they straight away got it straight away and it was really easy to use. And if you're new to coding, it's going to take you a long time to kind of get around how to actually run calculations, how to set up more complex calculations. And you might end up going back towards the GUIs or the Melts for Excel package and things like this. The main kind of idea or aim for developing PetThermoTools was to do that, to try and create something that it doesn't have all the bells and whistles that Enki has. It doesn't have all the kind of flexibility that Enki has, but has a significant proportion of that, but remains very accessible and easy to use. And so trying to kind of streamline those installation processes, which most people seem to have no issues with, which is great. It's kind of a major part of that, but also writing up functions so that you don't have to worry about the underlying kind of code packages in order to run thermodynamic calculations is another thing. And so primarily, as indicated here, PetThermoTools is built on Alpha Melts for Python. So this is Alpha Melts, once again, introduced earlier by Paula. This is kind of the main underlying code package behind PetThermoTools. And really, when we kind of dive into it in more detail, it's actually these Alpha Melts Python releases that are actually being used by PetThermoTools. And so in that install Alpha Melts function that you all ran to install this onto your machine, what it's actually doing is it's looking on your machine and saying, am I Mac, am I Linux, am I Windows, finding the correct zip file from Paula's GitHub repository, downloading that, and then extracting that onto your computer. And the idea with PetThermoTools is once you've done that installation script, all you need to do is specify a function. So here I'm showing isobaric crystallization. We can say a model, a starting composition. I want to start at the liquidus. I want to run at 4 different pressures. I'm going to buffer at FMQ. I have initial water CO2 content. So various, hopefully relatively logically labeled input parameters to each of these functions. That's all you need to do in order to run isobaric crystallization. You just need to import PetThermoTools as PTT, define a starting composition, and then run this. And we're hoping that's made it far simpler and more straightforward in order to actually run these calculations in a Python environment. And one of the advantages for that is we can also provide inbuilt plotting functions. So here we actually have a Harker plotting function. I'll show you guys this later, where we can plot our thermodynamic results. This is the results equals tab here. But we can also plot other data. So I'm loading in a melt inclusion and a matrix glass data set. And you end up being able to produce plots such as this. So we have our thermodynamic model predictions plotted against the data that we're supplying that we're comparing to these models. And the idea is to try and make this as contained as possible, to try and provide as simple a kind of workflow as possible for people using PetThermoTools or melts more broadly in their calculations, in their workflow. And so everything that we do, the idea is to try and make these kind of functions as easy and as logical to use as possible. So adiabatic mantle melting, you can see the result of this function on the right-hand side. This is a phase plot from a mantle melting model. Hopefully everyone's done the pip install PetThermoTools. After that, we can import PetThermoTools into our Python environment. If you need to, you can then run this import sys.path_append to make sure those alpha melts files are on the Python path. And after that, the only other thing you need in your code are these 2 lines. So the adiabatic decompression melting function, we should use pmelts. Remember what Paul spoke about earlier, how pmelts was calibrated based on Lurtzolite experimental data for pressure between 1 to 3 gigapascals. Well, that looks reasonably good for what we're looking at on the right-hand side. We have some saved bulk compositions. So the KLB1 peridotite is a saved bulk composition. Potential temperature, and the information about your pressure and pressure step within the model. That will run. And once again, we provide some inbuilt plotting materials. So we have a phase plot. We can say we want to plot the results and we want to plot it with our y-axis as pressure. And that's all you need. Those, what is this, 6 lines of code or something in order to produce a plot such as this, a prediction of your phase assemblage during mantle melting or adiabatic decompression melting. So the idea is here that we're hopefully taking alpha melts for Python, which is an amazing resource, and making it easily accessible, hopefully for anyone to be able to use. And this is really one of the first workshops we've done on this. And so any feedback you guys have is really, really appreciated. I realize there's still quite a way to go to make things exactly as we want them to be. But any feedback we have, anything that didn't quite work correctly, anything like that helps us improve it for the future. This is a kind of schematic that is available on GitHub of the various different functions that are currently available within PetThermoTools. So you can see basic isobaric crystallization, run at multiple pressures. You can see we have some polybaric crystallization options. Isochoric, once again, Paul talked about this earlier, so where we hold volume constants rather than pressure. Phase diagrams is quite a common use of PetThermoTools. Melting, and then what you're currently running is this one down here, the saturation pressure calculation down here. And there are various other functions that are included in PetThermoTools. Once again, check out the reader docs to learn more. And we're actually still kind of working on developing both more functions and also adding functionality to the existing things. For example, the adiabatic decompression melting function currently only takes 1 component, 1 lithology. I'm currently working on doing this so we can load 2 or 3 different mantle lithologies into a model and then run them at thermal equilibrium during adiabatic decompression. So you can simulate what would happen during decompression melting of a multi-lithology mantle, things such as that. The other thing that I'm actively working on developing is incorporating certain kind of like methods into PetThermoTools. So this one is a olivine spinel oxybarometer, which came out last year from Aaron Bell. And they basically used melts to predict the chemical potential of it was between olivine and spinel, the ion components, and using this to work out the oxygen fugacity of the system. They actually found they needed to modify some of the chemical potentials from melts in order to match the chemical data. But even still, it should be relatively straightforward within PetThermoTools to kind of recreate this method and provide a function where all you need to do is provide a data set of olivines, a data set of spinel compositions, and a melt composition, and then predict oxygen fugacity for your system based on this approach. So we're continuing to expand as more kind of methods develop, continuing to expand and try and incorporate these into our workflow. I'm going to go back to this page quickly, because one thing I kind of skipped over a little bit, and this starts to kind of really relate to what Paul spoke about earlier, is one of the really big developments that didn't happen initially with PetThermoTools, but came on a little bit later on, was the fact we realized that once we got this set up, and we kind of set it up just as a separate package that called the alpha melts for Python source code, we didn't have to purely rely on alpha melts or melts anymore. And this kind of came along back in 2022 when Mage Min got released by Nicholas Reel, and Nicholas has agreed to come and talk to us tomorrow about Mage Min and how it was developed and kind of the benefits and potential drawbacks that you might have using Mage Min itself. And Mage Min is written in C with wrappers and Julia. Don't worry if you don't know exactly what all this means. But we also worked out that actually, with some challenges, we could try and call the Mage Min Julia wrappers from Python. And as some of you have seen, this isn't the most straightforward thing. There are still some bugs in the installation process. Setting up that connection from Python to Julia has been quite challenging. We are slowly getting towards a point where I'm more and more confident that it is working reliably, but there's still a little bit of way to go. But the really important thing here is by doing this in PetThermoTools, we've potentially got the first time ever where you can directly compare different models within a single Jupyter notebook. Within a single environment, you can take one set of code. So here, once again, we're using adiabatic melting as an example. And this code here, I've got two different models, so pmelts and the Green et al. 2025 thermodynamic model. What this code is going to do, it's going to loop through those two models. So the first run will run the calculation with pmelts. The second will run it with Green 2025. So in the first run, we'll run adiabatic decompression melting with pmelts. In the second run, we'll run it with Green 2025. Every other parameter in here stays the same. Even though alpha melts and Mage Min require very different input structures in order to run calculations, what PetThermoTools does is allow you to use one input function, and then it redistributes that material so that it's understood by either alpha melts or Mage Min, runs the calculations, and once the calculations are done, it's returned back to PetThermoTools, and it once again will reorganize the output structures in this case so that they have the same format on the output. This means that you can use it regardless of whether you use Green or pmelts. You can once again use that phase plot function to create a plot such as this, looking at the predicted phase assemblage of the mantle during adiabatic decompression melting in a system that might approximate the conditions we'd expect beneath a mid-ocean ridge in this case. The other kind of major benefit I see of PetThermoTools is by writing it in Python, we've also been able to integrate with other Python toolkits. So once again, here's the isobaric crystallization function. Once again, specify the model, starting composition, what pressures do you want to use, oxygen fugacity information. One of the really nice things with PetThermoTools is the outputs are designed so that they integrate with other models. So we have, as I spoke about earlier, the inbuilt plotting tools, the Harker function, and things such as this. But we can also use our outputs to calculate things such as sulfide content at sulfide saturation. Sulfur content at sulfide saturation, I always get that wrong. This is using Penny's package PySulfSat, and basically by using a consistent naming convention, you don't have to kind of modify or adjust your output variables here. You can just take the outputs and provide them directly to PySulfSat, and it will calculate things such as the sulfur content at sulfide saturation. You can also take those outputs and provide them directly to Thermobar, which some of you may have used in the past, and it will do things such as plot up mineral compositions using things such as the pyroxene quadrilateral, or plot plagioclase compositions on a plagioclase, or sorry, on a feldspar ternary, things such as this. So this is kind of like some of the motivation and reasoning behind continuing to develop this package, is we're hoping it can provide a way for melts or thermodynamic calculations to kind of just fit in, to slot in with the rest of your Python workflow. If you're doing work in Python, you can just slot your melts calculations in, calculate your SCSS or whatever. Whereas previously you would have had to have run these calculations separately, save the text file, load the text file into your Python environment, and then do a further calculation on that. So the idea is it's now easier, you can keep it all in one place, and it all interacts reasonably well. I had a question the other day. We also have some examples of interaction with Pyrolite and doing TAS plots with Pyrolite. There's an example of that on Read the Docs that you might want to check out. Okay, I have a couple more slides, and this really goes in now to the main point that Penny wanted me to talk about. And this kind of starts to relate to that timeout function that Penny mentioned. Okay, so as I said, the initial idea of PetThermoTools was to base this on the AlphaMelts package. And AlphaMelts is an absolutely amazing package. But as has already been indicated several times today, when you run thermodynamic calculations, sometimes they crash, sometimes they don't work. And that doesn't necessarily mean that your system can't hit equilibrium. It just means that there was a kind of error in the minimization routine and an equilibrium state to the system was never achieved. And that's a natural part of doing thermodynamic modeling. Okay. One of the challenges, though, with alpha melts for Python specifically, is that because of the way the melt C library is loaded into Python, is that if a failure occurred, you couldn't then reload the melts library. It would print you these two messages here. And so this means that if you were using alpha melts for Python and you ran a calculation, and that calculation hit a failure point, and you then wanted to run a second calculation, you couldn't just go on to run the second calculation. You would have to restart your kernel, load in all the information you'd done before. So you'd loaded in a spreadsheet with potential starting compositions that you were slowly testing. You have to restart your kernel, go back to the top, reload in all your packages, load pandas again, load numpy again, load in your compositions, and then try your second composition. Okay. And it was actually for that reason that was the initial motivating factor for me to start developing PetThermoTools. I was using alpha melts with Python in some of my research, and I kept running into this error. I kept having to restart the kernel, and I wanted to see if I could find a way around it. And we kind of did. And the way we did this was by the use of parallel processing. And so imagine you are setting up a calculation with 4 separate fractional crystallization calculations going on. Okay. The way you traditionally do this, if you're using alpha melts for Python or alpha melts for MATLAB or even melts for Excel, you can do this in, is you would set up your calculation. You would tell it what compositions to use, what pressures to use, what oxygen feed gas to use, what water constants you want to use, everything like this. The system would then go and run melts calculation number 1. Once it's finished, it would then go and run melts calculation number 2, then number 3, then number 4, and hopefully everything works perfectly and you get your calculation results and you can go plot them up or combine them with other tools to learn more about your system. And that's the ideal way it would work in theory. The problem I kept running into is, well, calculation number 2 failed. And so I would set up a run of, sometimes it was much more than this, sometimes it was a couple hundred calculations, and go away to go grab a coffee, come back, and the third calculation had failed and everything else had just stopped and hadn't continued. And that's because of this reinitialization error that once run number 2 finished or errored, run 3 couldn't run, and run 4 couldn't run as well. So if I was lucky, I might get results back from run number 1. That was it. What we do instead is we run these calculations in parallel. So we set up our calculation in the main Python process. We then generate new processes, new Python processes that we actually run the calculations in. This has a little bit of overhead associated with it. So there is a bit of a slowdown in terms of how quickly you could run a single calculation because of this, because we need to generate these new Python processes. But basically what we do is we set up our calculation in the main Python process. We then send our information out into what are known as child processes. And these child processes are actually where the calculations are run. Now this has several benefits. It means that once they all finish, the information is sent back to the main process and we can plot up our results. But it also means that if run number 2 errors and fails, that's fine. Run number 2 has failed. But run 3 and run 4, they are happening in separate processes to run number 2. So they're going to keep running regardless. They don't care that run number 2 has failed. They're happening in isolation from each other. And so this means that even if run number 2 has failed, we would get results from run 1, 3, and 4, and potentially even from run 2 up until the point of failure. The other benefit to this is we can run these models simultaneously. This means that if everything works perfectly and everything runs as it should without errors happening, this can actually significantly speed up your calculations. So by running these things in parallel, we've actually done some tests and shown that with most kind of personal laptops, you can typically run 8 calculations at a time. Most of your laptops will have 8 logical processors on them. If you're working on a high-powered PC with like 32 logical processors, you can get a more significant speed improvement than this. But typically, we can have a between 2 to 4 times improvement in the speed of calculations when running large numbers of calculations compared to running them all sequentially. As I said, when running a single calculation, we actually have a slight speed penalty by setting up this child process. But when you run 8 or more in this case, you can get quite a significant improvement in the speed of calculations associated with this. And so how does this relate to the timeout function? Well, let's go back to our example where run 2 doesn't finish, right? So what's actually happening in the calculation that you guys are all running in the background whilst I'm nattering on is you have, I think it's something like 64 different melt inclusions that you're trying to calculate the saturation pressure for. What PetThermoTools is going to do is it's going to take those 64 calculations, and let's say you're working on a typical laptop, so you have 8 logical processors available on your laptop. It's going to take those 64 and it's going to split them into 8 groups. And each of those groups are going to be sent to one of the respective processors in a new child process in order to run the calculations. Okay. Now, these calculations are going to run, and let's say once again that one of them hits an error. If it hits an error, that's annoying, yes, but it does sometimes happen in thermodynamic modeling. The problem we've found is that we can't always catch the errors in PetThermoTools. So sometimes the error will happen within the C code of the melts calculations, and it doesn't automatically provide an error to Python. It's kind of almost gets stuck sometimes in this infinite loop within melts. And that's a problem because it never returns an error message in Python. So if we just let it run, it would run forever, just continuously looping through itself and never actually returning information to us in Python. So the timeout function is there to catch that. And the timeout function is telling it, how long do I want to wait for before I assume my calculation must have errored out and I just haven't got that information back. Okay. So deliberately, the function that we're getting you guys to run does actually have a case where one of the functions errors out on the first pass through, and it hits that timeout function. And so the timeout is the timeout per calculation in a process. So I said there are 8 calculations within each process in this example. So if you had your timeout at 5 seconds, it would be a 40-second timeout for the overall calculation, something like that. We set the calculation timeout at 45, and having a longer timeout is generally safer. It might mean that it takes a long time for the system to hit the timeout, but it provides more time to make sure the calculation does run if it can. Okay. We don't want to set the timeout too short, and we cut calculations off before they finish and we don't get any results. So it's better to be patient sometimes, leave a longer timeout, even if it means the code is slightly slower, but you get more calculations back. And so what I'm actually going to do here is I'm going to quickly pop over into the example that you guys are all running and talk through exactly what's happening with respect to this example here. So this is the calculation that's going on, okay? And so this is 64 melt inclusion saturation calculations going to be split across 8 separate child processes. And what I like to do when doing this is actually I like to track what the CPU usage is doing. So I'm going to hit run on here, and I'm going to open up the activity monitor and go to CPU. And you can see that as soon as I hit run, the CPU usage jumped up to 100% essentially, and a bunch of Python processes got initiated. These Python processes are now going to start actually being completed as they finish their runs, and the CPU usage is going to drop back down towards a lower level. And at this point, the calculation is still running. So the CPU usage has dropped down, and there's no Python process with a really high CPU usage in here. And that's because all the calculations have either completed or they've hit one of these errors and we're waiting for the timeout. So the timeout is currently on 45 seconds. This is multiplied by the number of processes within a run. So this might actually take a couple of minutes before we catch that timeout, okay? So this is like when I'm doing calculations and I'm trying to work out what timeout I need, I do sometimes use the activity monitor or task manager on Windows to look at that CPU usage and see, is the CPU usage decreasing back down towards the kind of like background state? And if so, that's kind of my estimate of how much time is required as a minimum for the timeout because otherwise, if I set it shorter than that, I'm going to cut off calculations before they finish. As default, you don't really have to even worry about timeout. As a default parameter will be set to quite a long time in your calculation. But if you're trying to do things quicker, it's something you might want to adjust in order to kind of like remove this kind of empty time that things are going on, even though that things are going on whilst you're kind of waiting for calculations to take place. Okay. So at the moment, I say on my Mac is significantly quicker than Penny's laptop. So this timeout was actually set for Penny's laptop where things take much longer. I, for this calculation on my Mac, would have maybe set the timeout to 10 seconds. And it just reduces this kind of wait time in here. But whilst it's going on, basically what the system is doing is the rest of the calculations are running. So actually on the Discord, Stephen has posted a screenshot. So completed 82%. That screenshot on the Discord that Stephen has just, I apologize, I'm pronouncing your name wrong, I just posted, is exactly what I would expect to see. You will only see this on Windows though. On Mac, you won't see this because on Mac, we suppress the outputs. And so this is something you will see on Windows. You won't see on Mac, I'm afraid. But that basically said, on the first attempt, 82% of those melt inclusions will manage to find a solution for. What it's going to do after that point is it's going to take every melt inclusion where we didn't find a solution for and didn't return an error. So everything that returned an error is going to be put in a separate pile. Everything that we didn't get around to calculating. So imagine you have 8 calculations in a process. Calculation 3 fails, so 4, 5, 6, 7, 8 never got calculated. Those final calculations are going to be redistributed across the child processes, and we're going to try again. So that second step of 98% complete, that's basically saying everything but one calculation completed. And then finally, on the third attempt, 100 calculations are complete, but 3 of them failed, is what that's saying. What this saturation pressure calculation does is it says, okay, I had 3 failures. Let's adjust some input parameters. Let's change the initial pressure or initial guess and see if that allows us to find a solution. And this is important because it actually, as Paul was talking about earlier, when things crash, it doesn't necessarily mean that that system can't ever find equilibrium. Slight subtle changes in the starting guess can actually sometimes lead to you finding an equilibrium point for that calculation. Okay. And so hopefully everyone has, but given I've been talking for quite a while, been able to run this calculation and being able to run this calculation and run this cell here, which should print the output data frame. So the data frame, which is outputted, and you should see a column for P bar and T lick C. These are the 2 kind of outputs from those calculations. The pressure.
I will interrupt at this point. Some of you, it will possibly not have finished. And just as a justification, this is one of the slower calculations. It's also because we're all running Zoom and Discord. So I will tell you that this calculation took 6 minutes when I ran it last night. My laptop has now been running it for 30 minutes and it still hasn't finished. And that is a sheer function of the fact that Zoom is sucking up the vast majority of my laptop's ability. So for those of you who probably spent less than $1,000 on a laptop like me, don't take it personally. This is the kind of thing where if you are running these calculations, I would recommend closing all of the things on your laptop, which are doing big thinking like Zoom, Discord, everything else you've got up, or possibly running on a desktop. These calculations are slow when you run them on the Yankee server as well. Saturation pressures are quite hard to get, but I have not finished. Out of curiosity, could people please post in whether they have finished or not finished? And also, if you know what your laptop is, if you could post that as well. So if you know you have a Mac M4, for example, from 2025, that's good for us to know, just because this is basically an indication of who spent a lot of money on a laptop and who didn't. So yeah, this failing thing that Matt talked about, this is actually something I asked him to add 2 days ago. This is basically because those of you who have done melt inclusion work know how heartbreaking it is that you've spent hours on 2 melt inclusions, say you've double polished them for FTIR, like I know Heather's done some of, you've ramened them, and then it doesn't converge. You've put all this effort in and you don't get a saturation pressure. So although it's slowed down, The idea is it might for many of these actually eventually find a solution, but it's adding a big time penalty. So for those of you who are seeing that attempting to resolve these failed calculations, that is a function of the fact that we've decided it's more important to have successes than failures. I'm also just wondering, Matt, is there any way, has yours finished?
No, I'm going to try it again with a reduced timeout to see if I
How
can.
long is, can you just check how big that Aleutians data frame is? Because I'm just very suspicious that this version we've given people isn't the version that.
No, it's the same.
No,
Same
it's the
size.
same. Okay, yeah. So basically, and the fact that they're returning different failed calculations. Maybe Paula, this is for you to step in. So do you want to talk about the inherent randomness in melts and why a calculation might sometimes run and sometimes fail? Oh, I don't know if we've lost Paula. Maybe we've lost Paula. She can talk about that later. Oh,
Yeah, no, I haven't got the decent microphone at the moment. I don't know. Um, I'm not quite sure. I need to think about what to say.
sure, we can
Yeah,
get back to
and
you on
maybe
this.
yeah. I've just been answering something on Discord, so um, but also maybe Paul has like thoughts.
Yes.
It is interesting that Heather,
Yeah.
for example, I'm surprised Heather had 53 failed. How many, if people could, oh, I guess those of you on Macs don't know how many failed calculations you have, but if those of you on Windows can just post in the chat, that is useful for all of us to have. And we'll see whether I
Everyone with the
truly.
M4 chips is showing off right now.
Yeah, the most
Right.
I've always hated Mac, and this is the one thing that's really making me want to buy a Mac, everyone, is that it has just got ridiculously fast compared to our normal Windows PCs, which I'm finding very, very frustrating.
Yeah, so I would expect 2 or 3, based on the tests I did yesterday, I would expect 2 or 3 failed calculations that are resolved in the next step. So that's what a couple of people currently posted.
We'll have to work out exactly what's happened with
I
Heather's.
don't know, and Brad had that as well, 26 failed.
Yeah.
I'm
So
not quite
we
sure.
think there is some inherent randomness. We're still trying to get to the bottom of this. This is super helpful. Those of you who are posting 2 failed calculations, could you edit your thing so you know what computer you have, if possible? So Dawn, yours is because it's failed for 50 calculations. So there really is some randomness here, Matt, isn't there? The different people's
Unless if
computers
it's
pick it up.
just that it's timing out
Oh,
on
the
them.
timeouts are
So
too.
like
I think
it might be if you guys have if your computers are just really struggling with Zoom, Discord, and everything going on, it might be that the timeout needs to be set at like 180 or something. It might then take a long time to finish, but it would return results. It's very frustrating that there's this much difference in time between different computers, but it does seem like yeah, there's a benefit sometimes to putting the timeout longer.
I think you're right, Matt. That must be what's happening to mine and why it's taking so much longer. So basically, those of you who have Windows computers, I'm sorry, it can't handle the Zoom, the Discord, and this.
It's not just Windows though, because Matt has just posted he's got Windows done in 3 minutes and no
But he probably
failures.
has a fancy. If you have a cheap
I think
Windows laptop, this is the point at which you're going to
Yeah.
start struggling, I think.
yeah, I think it's how much memory you've got, you know,
Yeah.
what the
Yeah.
and also like um I've kind of stopped testing things on Windows 10, except, you know, when somebody specifically says they're on Windows 10. So um yeah, so some of the older laptops it might be, you know, might in theory it should work on Windows 10, in theory it should work on you know, as well on Intel Macs and things, but obviously we devote more of our time making sure things work on the newer operating systems. And
What I would suggest is those of you who it's still running for, just leave it running. We'll go through the next bit using Matt's laptop because Matt's yours is finished now, hasn't
Mine's
it?
finished, yeah. Yeah.
And what I'll basically tell you is like, yes, this makes it look really slow, but if you close Zoom, close everything else and run it, my laptop is like slower than all of yours because I've not even got to the same print messages as you, and yet it ran fine when I wasn't doing all this stuff. So we'll just plow on. I apologize on behalf of those with slower laptops, but it will work much better when you're not running Zoom. Okay, so Matt, do you want to keep scrolling down?
Yeah, sure. What I will quickly do is I'm going to throw in, so one of the keyword arguments in this file that we aren't using, because by default it's set to 2, is this max retries thing. And if I set this to 0 and run this, you'll see what used to be returned before Penny got me to change this. And so this retries is like how many times once it identifies a failed calculation. At present, this is only the case in saturation pressure calculations, not in anything else. This is like how many times it will adjust those input parameters and search again for a solution, essentially. So if I run this one now, and once again, if I look at the activity monitor, you can see the calculation started up. This time only took 23 seconds, but you see calculation number 5, one of these melt inclusions return NANs. So that max retries as default is set to 2. And that's basically saying that in that case, I'm going to adjust the starting parameters. It will, I believe the first time it will reduce the starting pressure guess by 20%. If that doesn't work on the second retry, it will double the starting pressure guess from that initial 20% reduction. So it's just going to adjust those initial parameters. And you can see that by adjusting initial parameters, you kind of like get yourself out of this kind of melts hole where it doesn't know how to kind of find a solution in. And you can sometimes end up getting a real answer from your calculation.
Matt, can you not run? Because now we've got to wait for this to finish, right?
It'll only take another minute.
Okay, so we can scroll down. So basically the outputs, you can see that what it's done is it's returned like the saturation pressure data frame. So you've got your volcano and your sample. Matt, if you scroll up, that is because you've asked it to copy the columns volcano and sample over from elution. So by default, what this function will return is all of the oxides, so the major elements, the volatile elements, the pressure and the temperature. And in this case, you've copied volcano and sample over, so they're appended on that SATP. So Matt, if you just scroll to the right of your SATP data frame.
Yeah, 1 second.
So you can see that P bar, that is your pressure or vapor saturation, and then that T lick C, that is the liquidus temperature that Meltz has calculated. Okay, so then if you scroll down, so what we can do is we can make a violin plot that shows the pressures. And again, once those of you who are running on slow laptops do this without Zoom, you'll be absolutely fine. So if you just go down to...
Yeah. So I'm just going to point out that with the max retries 2, that 5th sample now returned a pressure.
So although this is slower to do the max retries, again, you've spent hours on that individual melt inclusion. So that's why this is a calculation where it's worth trying to get all of the results back that we can. So you can see these are the pressures that you would get in that violin format. So again, as we could have predicted, Augustine has higher pressures because it has that higher water and that higher CO2 content. So if you keep scrolling down, Matt. So then you could make, if you have... if it has finished for you, you can just quickly adapt this plot to show it for estimated temperature. So Matt, do you want to just do that so that people can see? And again, they can run it when it's not being so slow.
Yeah, so all I did there, copied the code, and it's just the wide parameter that's changed because it's calling from that data frame. So all we need to do is make sure that what I'm giving it here matches the column header in the data frame here, the tlick_c, and then you can see the kind of results in here.
Okay. And then Matt, if you keep scrolling down, I'm just restarting my kernel so that I can do the next bit. Okay, so another thing that we could do is part of the time that this calculation is spending is calculating the liquidus temperature. It's basically doing two things to try and find where you are. You could speed this up by using an empirical estimate of the liquidus temperature. So I don't know if Keith is still online, but Keith Paterka came up with this great equation, equation 22. This is from his 2008 review chapter. This is actually, it was an olivine liquid thermometer, but you can actually replace the dependence of the olivine using the DMG partition coefficient between olivine and melt. So this is basically a melt thermometer based on an olivine melt thermometer. Matt and I did some tests for a review paper that we can send around that actually showed for arc magmas across a surprisingly large range of silica contents. This was the best thermometer that we have. So this is where we have this advantage that Thermobar, which is the thermobarometry package I wrote, and PetThermoTools have the same input structures because it means we can use these empirical guesses. So here what we're doing is we're calculating temperature using the Thermobar function, calculate lick only temperature. If you've never used Thermobar before, you'll need to uncomment the line above. So Matt, can you just show them how they would do that on the pip install Thermobar line? So you would just delete that hash, run that. That would then get you Thermobar. You then need to import Thermobar. And then all you give Thermobar is your liquid composition, so that is your elution data frame. You specify this temperature, which is this equation 22 BTDMG, and you specify a pressure in kilobars. It's really not that sensitive to pressure, so don't stress about this. And then the final thing you need to do is subtract 273.15. That is your temperature, because it's Thermobar returns in Kelvin by default. So then you could then run this again. We're not going to run this, Matt, so don't do this because I want to get on to the rest and we've got lunch planned.
It should only take a minute. I'm going to run it while you chat.
So here, what did you do?
I didn't run that.
You didn't run that. There we go. So now instead of that other T parameter, you now have T fixed C, and you're going to set that to that calc T parameter.
Yeah. So just to specify the difference, everything else has stayed the same. It just previously we were specifying an initial temperature, and then it was iterating in both temperature and pressure to find the liquidus at fluid saturation. Now we're saying, okay, fix the temperature at 11 seconds. And yeah, so saying fix this temperature and just search for pressure. And importantly, in this calculation, it actually turns off all solid phases in melts. Because you want to know the solubility in that liquid composition, and you're saying, I know the temperature, just give me the pressure, it turns off solids so you don't accidentally crystallize a bunch of feldspar or something. So it's purely a liquid fluid equilibrium in this calculation. So it's slightly different to what's happening above. And you can see this took 11 seconds. This calculation took 1:30. Otherwise, they're identical. But yeah, so you can significantly speed it up. And hopefully there's no nans, which are not. It's the same output structure down here.
Okay, so then what I've done, Matt, go back up to the, no, there you go. So at the bottom here, I've just made a new column. So sometimes when you're working with data frames, you're going to want to like save all the columns in one place if you want to compare them. So you're on line 14, you can say, I've made a new column, P-bar calc using the liquidus temperature, and I've taken that previous data frame SATP and appended that on. I've then also appended the temperature that it's calculated. And then I've now added two more columns. So P-bar calc Peterka 2008 T. That is the pressure calculated using the Peterka thermometer, and also the temperature that the Peterka thermometer calculated. So now we've got them all in one place. If you keep scrolling down, Matt. Now what we're going to do is we're going to make a plot, and you can see this is a slightly different form of subplots. This just shows the diversity of Matplotlib. We're setting up two axes. We're calling them AX1 and AX2 now. And we're going to plot the temperature that is the liquidus temperature from melts versus the temperature that was calculated using Keith Peterka's thermometer. And then also we're going to plot on the second thing, the pressure calculated using the liquidus temperature and the pressure calculated using the Peterka thermometer. So if you scroll down, Matt, what you'll see is that melts is tending to give higher temperatures than Peterka. And this is something that Paul mentioned in his little intro. This is kind of a known flaw with melts. Melts will often overpredict the temperature. What you can see on the right-hand side is that even though this saturation pressure calculation is being done with temperatures that differ by 100 degrees for some of these, the effect on pressure is very small. And this just shows you that in the grand scheme of things, saturation pressures aren't that sensitive to the temperature. So you don't need to stress super much about what thermometer you're using. If you keep scrolling down, so what we did to assess this is we actually took a load of experiments that weren't used to calibrate many of these thermometers. And that is because simply they did not make it into the library of experimental phase relationships. They have been published since. So these are ARC liquids, where we know the temperature, we know the pressure, we know the oxygen fugacity, and then we basically tested how different equations do at predicting the experimental temperature. So you can see on the top left in this screenshot, this is that equation 22 DMG calc. And even though this was only calibrated for olivine, you can see it really does do remarkably well across the entire range of liquids. The coloring here is the silica content of the liquid, so it's going up to 80% silica, and it's honestly amazing. On the right-hand side, we have the P-Melts liquidus. So it's not bad. You've got a bit of a offset to higher temperatures, but not nearly as significant. And then on the bottom left is Melt V 1.0.2. 1.2.0 is actually very similar as well, and we show that in the supplement for this paper. And what you can see on the left-hand side, Matt, if you put your mouse over there, consistently Melts is over predicting the temperature for these experimental liquids. So this is fine. Just be aware that when we are working in Melts land, our temperatures might be 50 to 100 degrees hotter than reality. Mage Min actually shows an even bigger offset towards these higher temperatures when we did these tests for liquidus. So in general, when you're doing saturation pressure calculations, I would honestly advise you use an empirical thermometer instead, because it does a better job of getting the true experimental temperatures.